Good afternoon, everyone. We will start with the third session, which is the physics. So, during the last session, we have seen the chapter 1 of the 12th, which is the rotational dynamics. In this session, we will study the mechanical properties of the fluid, which is the chapter 2. So, this is the overall content of the chapter 2. So, the first we have different states of matter. So, in that we have solid, liquid, and the gas. Then we will study the fluids and its properties. After that, pressure and the Pascal law. Then we will see the applications of the Pascal law. So application involves the Pascal law used in the hydraulic lift and the Pascal law used in the hydraulic brakes. Then we will study the different pressure measurement devices. So in that we have the mercury barometer and second one is the YouTube manometer. Then we will study the surface tension and the surface energy, angle of contact, and shape of different meniscus. So we will see the concave and the convex meniscus. Next, shape of the liquid drop on the solid surface. And after that, we will study the capillary action. The next section is the fluid motion. So in the fluid motion, we will study different fluid flow properties like flow lines, streamline, flow tube, then types of flow, which is the laminar and the turbulent flow, etc. Then we will see the critical velocity and the Reynolds number. So last we will study the viscosity and the Stokes law. Then we will see the continuity equation for the fluid flow, Bernoulli's equation, and application of Bernoulli's equation for the flow measurement devices, which is the venturimeter. Okay. So this is the overall content of the chapter 2, which is the mechanical properties of the fluid. In today's session, we will just revise the concept up to the capillary action. Okay. And in the next session, we will study the fluid motion, viscosity, and the Bernoulli's equation. So the first point is the states of matter. So as we already studied, there are three states. One is the solid, liquid, and the gas. Okay. So solid means it maintains fixed shape and the volume when a large force is applied to it. Liquid and gas do not have their own shape and takes the shape of the containing vessel. They have no rigidity. Now fluids, its definition is a substance that can flow is called as a fluid. So all the liquid and gases are referred as a fluid only. Okay. And the fourth state of matter, which is the plasma, it is also included in the fluid. So the ideal fluids are the substances which cannot resist any shear force applied on it. So for the ideal fluid, shear modulus is 0. Okay, this is for the ideal fluid. So what are the properties of the ideal fluid? First, it is incompressible. Second, its flow is arotational. Third is it is a inviscid, so it has no viscosity. So viscosity is 0 for the ideal fluid. Flow is steady. It means flow is not changing with respect to time. So flow is not changing means it's a velocity or the acceleration. They are not changing with respect to time. Next is ideal fluid do not offer any shear resistance as they don't have the viscosity. So shear stress in the ideal fluid it is 0. and they can be subjected to normal compressive stresses called as a pressure. Okay, so ideal fluids, they are only subjected to pressure, which are the normal stresses, and the shear stress in the ideal fluid is 0. So tau, it is equal to 0 for the ideal fluid. So these are some properties related to ideal fluids. Next is the pressure. So pressure is nothing but force per unit area, and its SI unit is Newton per meter square. Dimension of the pressure is L minus 1, M1, and T minus 2. So this is the dimension. For the pressure, we can use the unit bar or the Pascal. So this is the relation between bar and Pascal. So 1 bar, it is equal to 10 raised to 5 Pascal, and Pascal is nothing but Newton per meter square. So 1 Newton per meter square is nothing but 1 Pascal. And the kilopascal and Pascal, 1 kilopascal, this is equal to 10 to the power 3 Pascal, or 10 to the power 3 Newton per meter square. Now next is pressure due to the liquid column. So suppose we have one container. So we can consider this is a tank, and it is filled with the water or any other liquid. And this is the height of the liquid in that tank. So if you want to find out what is the pressure at the bottom of the tank because of the liquid. So at this point, let us take this point as A. This pressure is given by this equation. So pressure at point A, this is equal to density of the liquid into acceleration due to gravity into height of the liquid, which is above that point. So from this A point, measure the total height. So from this equation, we can find out the total pressure at the point A. Okay. So this pressure in the liquid, it only change with respect to the height h. It is not dependent on the area of the tank. Next, we will see the concept of atmospheric pressure, absolute pressure, and the gauge pressure. So what is atmospheric pressure? So atmosphere contains the air, and it exerts the force due to its own weight. Thus, the pressure due to force exerted by the air column, this pressure is called as a atmospheric pressure. The pressure below the atmospheric is called as a vacuum pressure. So atmospheric pressure, this is generally taken as 1.013 bar. Now what is absolute pressure? So absolute pressure at any point A is the addition of atmospheric pressure plus the gauge pressure. So P absolute, this is equal to P naught plus rho gh. This P naught is nothing but the atmospheric pressure. This atmospheric pressure, this is because of the air column, which is above that point. Okay. And PA is the absolute pressure, or we can say it is the total pressure, including air pressure. Okay. So this is P naught plus rho gh. And the gauge pressure is the difference of absolute and the atmospheric pressure. So if PA is the absolute pressure, let us take this point is A. And if you want to find out the absolute pressure at point A because of this liquid column, so first measure this height, which is the h, with respect to point A or the above the point A. Okay. And above this free surface of the liquid, there is air, and this air will exert the atmospheric pressure, which is the P naught. Okay. So total pressure at point A, this is called as absolute pressure at point A. This is equal to pressure because of liquid column. So this pressure is rho gh, this is called as a gauge pressure, plus pressure of the air, which is the P naught, that is called as atmospheric pressure. So this addition is nothing but the absolute pressure at the point A. Okay. So gauge pressure is nothing but the rho gh. So you should remember this difference between the gauge pressure and the absolute pressure. Okay. Absolute pressure means atmospheric pressure plus gauge pressure. Now, depending on the equation rho gh, which is the hydrostatic equation, rho gh for the pressure, we have the hydrostatic paradox. So, what is meaning of hydrostatic paradox? If you choose different containers, okay, having the different shapes, and if the liquid level is same in all the containers, then pressure exerted at the bottommost point of that container will remain same, irrespective of the shape of the container. So here I have selected 4 different containers. One is the two are conical, one is a cylindrical tube, and this is one is a spherical. Okay. The liquid column in all the container is having the same height, that is the h with respect to the bottommost point. So let us take this point is A, this is B, C, and D. Okay. So for all the point, pressure PA, pressure PB, pressure PC, and pressure PD, all these pressures will remain same. And this pressure, it only depends on the equation rho GH. It will not depend on what is the cross-sectional area. So this is called as a hydrostatic paradox. Next, for the pressure, we have the Pascal law. So what is the Pascal law? Pressure applied at any point of an enclosed fluid at the rest is transmitted to every point of the fluid and on the wall of the container. Okay. So Pascal law has application in the hydraulic lift and the hydraulic brake. So here I have shown one example of the hydraulic lift. So here in the hydraulic lift, we are using the cylinder and piston arrangement. So here we have small cylinder having the cross-sectional area A1, and at the second point we have the cross-sectional area A2, okay, which is greater than the A1. So if I apply the small amount of force F1 at this piston, we can lift relatively very high weight at the other end. So this is the application of Pascal law. So Pascal law here we can write pressure intensity, it will remain same. So P is equal to force upon area. So if you consider only this cylinder, which is a smaller cylinder, then we can write F1 divided by A1. The pressure is same, so it is equally transmitted to the other end. So at the second cylinder, pressure will remain same. So P is equal to F2 divided by A2. So we can equate these two equations. And from this, if the one force is given, which is the smaller force, we can find out the value of the second force. So F2 we can find out F1 into A2 divided by A1. Okay, so remember this equation for the Pascal law. Madam. Okay. Now for the pressure measurement, we have two devices. One is the mercury barometer and second device is the U-tube manometer. So mercury barometer is just a single glass tube. So we can measure the atmospheric pressure by using the mercury barometer. So this is the liquid in the mercury barometer. Just we have to measure the height. And by using this equation, P is equal to rho GH, we can determine what is the atmospheric pressure. So actually this is the atmospheric pressure which is exerted on the liquid which is in the container. Because of this pressure, the liquid will flow inside the tube and it will push to a certain height. Okay. And at this height, it will achieve the equilibrium. Okay. So this height measured, it will directly give the what is the atmospheric pressure. Okay. So just by measuring the height of the liquid rays in the barometer tube, we can determine the pressure PA, which is equal to rho GH, and its unit is Newton per meter square. So suppose we are using the mercury to measure the atmospheric pressure. So this liquid, let us take this mercury, that is the Hg. Then the height H, this is equal to 760 millimeter, or this is equal to 0.76 meter. Okay. So atmospheric pressure, it is expressed in terms of height of the mercury column. So this is equal to 76 centimeter, or this is equal to 760 millimeter of H. Okay, or this is equal to 0.760 meter. So this is the atmospheric pressure. Now anything below the atmosphere, okay, that is if the pressure is below the atmospheric pressure, so it is referred as the vacuum pressure. Okay, and unit to measure the vacuum pressure is the torr. So this is the relation between a torr unit and millimeter of Hg. One torr is equal to the 1 millimeter of Hg. Okay. Now next device used to measure the pressure is the U-tube manometer. Okay. So here you can see this is one cross section of the pipe, and there is one liquid which is flowing in that pipe. So this is in a 3 dimension. So liquid is flowing in this pipe, and if you want to measure the pressure of the liquid in this pipe, then we can connect one glass tube having the U-tube, shape is U-tube. Now it is filled with the mercury. This is called as a manometric fluid. So let us take, this is the Hg. Okay. So because of the pressure, the mercury in the left side of this tube will be lowered, and the mercury on the right side, it will be raised in the upward direction. Okay. So there is one level difference. So this is the level difference H. Okay. So by measuring this level difference, we can determine what is the pressure inside this pipe. So let us take this point as a PA. Okay. So we can select one reference line. So select this reference line, which is the lowermost point of the left side. So pressure along this line will remain same. So I will select this point as a 1 and take this point as a 2. Okay. So P1, this is equal to P2. So P1 means what? This pressure at the point 1 is because of this liquid, okay, and plus the pressure inside the tube or inside the pipe. So P1 is equal to PA plus pressure due to the liquid column above the point 1. And on the right side, we just have the mercury. So this is equal to pressure above the point 2. Okay. So PA is the pressure inside the pipe plus this is the liquid column which is above the point 1. So let us take this as a H1. So equation is rho G H1. This is equal to pressure above the point 2. So this height is H. So pressure will be rho. So this is for the rho mercury. And here rho, it is for the liquid. So let us take this as a water. So it is a rho W. Okay. So rho M G into H. So by using this equation, you can measure the height H, which is the level difference. We can measure the H1, which is the height of the liquid on the left side. And from this, we can determine what is the pressure inside the pipe, which is the PA. Okay. So here PA, this pressure, this is equal to rho mercury GH minus rho water GH1. Okay. So in this way, we can use the U-tube manometer to determine the pressure inside the pipe. Now next concept in the properties of the fluid is the surface tension. So what is the surface tension? It is defined as the tangential force acting per unit length on both the sides of an imaginary line drawn on the free surface of the liquid. Okay. So mathematically, surface tension is given by T is equal to F upon L. Okay. So F is the force acting on the imaginary line and L is the length of that line. Newton per meter is the unit. Okay. And dimension is L0, M1 and T minus 2. Okay. Now, what are the reasons for the surface tension? Intermolecular force. Okay. So first one is the cohesive force. So what is a cohesive force? Attraction between the molecules of the same substance. So if there is attraction between the molecules of the same substance, that force is called as a cohesive force. So this force is strong in the solid and it is weak in the liquid and the gases. Okay. So due to this force, solids have the definite shape. Liquid droplet coalesces into one drop due to the cohesive forces. So meaning of coalesce is if you have these smaller droplets like this, okay, they will combine and they will form one bigger drop. Okay. So this bigger drop is formed just because of the cohesive force. Second force is the adhesive force. So force of attraction between different molecules of the different substances. Okay. So this is called as the adhesive force. One example is water droplet sticks to the glass surface and it is because of the adhesive force. Okay. So if you pour the water in the glass container, then you can observe some of the water droplets are stick to the wall of the glass container and this is because of the adhesive force. So adhesive force, it is for the different molecules. Okay. Now for the surface tension, maximum surface tension is observed in the mercury and the minimum is glycerin. Okay. So here relation is given. Mercury has surface tension of 0.43, water has 0.072, and glycerin has 0.063. Now in the surface tension, we have one concept which is the range of the molecular force. So what is the range of molecular force? The maximum distance from a molecule up to which the molecular force is effective. So suppose we have one liquid and this is one molecule. Okay. So this molecule can apply the attractive force or attraction force for second molecule, and this maximum distance, this is called as a range of molecular force. Okay. And this range, this is up to 10 to the power minus 9 meter. That means if the second molecule is within this range of 10 to the power minus 9 meter, then this molecule, it can apply the cohesive force on the second molecule. So range of molecular force, this is up to 10 to the power minus 9 meter. So within this range, one molecule can apply the force on the other molecule. Second concept is the sphere of influence. So sphere of influence is an imaginary sphere with a molecule at its center and the radius equal to the molecular range. So if I take the same example, so if this is one molecule, this is the sphere of influence. For this sphere, this is the radius, and this radius, it is equal to up to 10 to the power minus 9 meter. Okay. So this is one imaginary sphere with the center, there is one molecule. Okay. So this molecule can attract any other molecule which lies within this sphere. Okay. So this is called as a sphere of influence. Okay. Next one concept in the surface tension is the surface energy. Now what is surface energy? Work done on stretching the surface film by the amount dA is stored as a potential energy in that liquid, and this energy is called as a surface energy. Okay. Its a mathematical expression is W is equal to T into dA. That is surface energy is equal to surface tension into change in the surface. So surface tension is also called as surface energy per unit area. Okay. So let us take this is the original film or the original surface. Okay. We are applying the force F and we are increasing the surface area of that film by the amount dA. Okay. So for increasing the surface area by the amount dA, the energy is stored in that film or in that liquid, and this energy is W is equal to T into D. So surface tension, this is given by the potential energy upon the area, or the surface energy upon the T. Okay. So we have work done in forming a liquid drop of the radius r and the surface tension T. So W is equal to 4 pi r square into T. Okay. So energy required to form a liquid drop. So this energy, or the work done W, this is equal to 4 pi r square into the surface tension T. Second, work done in increasing the radius of a liquid drop from R1 to R2. That means if you have one liquid drop having the radius R1, we want to increase the radius. So this is the bigger drop. Now the radius is R2. Okay. So the energy required to transform the sphere from R1 radius to R2 radius. So this energy is given, W is equal to 4 pi T into bracket R2 square minus R1 square. Okay. So note down these equations. Now the third equation is work done in forming the soap bubble of radius R. So work done to form soap bubble. So this is equal to 8 pi r square into the surface tension. Fourth is work done in increasing the radius of soap bubble from R1 to R2. So it is similar to this. If there is a soap bubble having the radius R1, we want to increase the radius to R2, then the total work done is, it is 8 pi T R2 square minus R1 square. Okay. Next we have work done to split the liquid drop of radius R into n identical droplets. Okay. So suppose we have one bigger drop and we want to transform this drop into smaller drop. Okay. So number is n. N can be 4 drops, 5 drops, 6 drops, 7 drops, etc. Okay. So this work done to convert single drop into multiple drops, this is given by 4 pi r square into surface tension in bracket n raised to 1 by 3 minus 1. And work done to form a bigger drop from n identical drop, that means in the reverse direction. We have smaller drops or the droplets. We want to combine these droplets into a single drop. Then the work done will be, so in this case work done is equal to 4 pi r square into surface tension bracket n minus n raised to 2 by 3. Okay. So this work done is converting multiple drops into a single drop, and this work done is for converting the single drop into multiple drops. Next, we have the concept of angle of contact. So in the angle of contact, first we have the concave meniscus. For the concave meniscus, the angle of contact is the acute angle. Okay, it means theta is less than 90 degree. So this angle is observed, which is the acute angle, for the liquid or the fluids which partially wets the solid surface. Okay. So example is the water and the glass contact. For water and glass contact, we can always observe the angle of contact is less than 90 degree, which is the acute angle. Okay. Second is the convex meniscus. So this is the convex shape. So in case of convex meniscus, the angle of contact is the obtuse angle. It means that theta is greater than 90 degree. And this is observed for the liquids which does not wet the solid surface. So in case of obtuse angle liquids, the cohesive forces are always greater than the adhesive forces. Okay. So here Fc is greater than Fa. And the example is the contact between glass surface and the mercury. Okay. So this is about the convex meniscus, which is the obtuse angle. Now here you can see the force P is the adhesive force, Fc is the cohesive force. So for acute angle, where theta is less than 90 degree, and the example is water and the glass contact, the relation between the force. So AP bar, which is the adhesive force, is greater than AC bar upon root 2. That is the cohesive force divided by square root 2. For obtuse angle, it means theta is greater than 90 degree. Example is mercury and glass. Here adhesive force is less than AC upon root 2, which is the cohesive force divided by square root 2. And if the angle of contact is exactly 90 degree, so this is for the liquid which do not wet the solid surface. Angle of contact is theta is equal to 90 degree. AP bar is exactly equal to AC upon root 2. And for the liquids that completely wets the solid surface, theta is equal to 0. And if theta is equal to 0, the cohesive force is 0 and adhesive force is the net force. So you can see this diagram. This is theta is equal to 0. Okay. Total force is nothing but the adhesive force. And this is the common tangent line to this liquid surface. And therefore theta it is equal to 0. Okay, so now we will solve some of the MCQs on the part that we have just covered, from the pressure up to the surface tension. Okay, so this is the first objective type question. So this is on the pressure and the Pascal law. So question is, the pressure at the bottom of a liquid tank is not proportional to the, so we have to select the correct statement. Pressure is not dependent on the acceleration due to gravity, density of the liquid, height of the liquid, and last is area of the liquid. Okay. So the pressure because of the liquid column, let us take this is a tank, and this is the liquid. We are selecting one point at the bottom. So pressure at this point, it will only depend on this height. It will not depend on what is the area. Okay. So we have the equation, pressure is equal to, this is called as the hydrostatic pressure, density of the liquid, acceleration due to gravity, and the height of the liquid. Okay. So correct answer for this question is pressure at the bottom of the liquid tank is not proportional. Okay. Not proportional means it is not dependent on which quantity? Area. Okay. So correct option is option D. So pressure is dependent or the proportional on the density. Pressure is proportional on the acceleration due to gravity, and pressure is proportional on the height. Okay, refer the second question, which is on the Pascal law. So question is, in a hydraulic press, F and F are the forces acting on the small piston and the large piston, having the diameters D and capital D respectively. Then the ratio F upon F is equal to. Okay. So this problem is based on the hydraulic press. In the theory, we have just seen the basic formula. So this is the smaller piston and this is the bigger piston. This is the force, which is a small f on the smaller piston, and the force generated on the other side is the capital F. Okay. Pressure intensity, it will remain same. So pressure here is P. So P is equal to cross section area is, let us take A1, and this area is A2. So pressure is force upon area. So smaller piston is force upon area A1. The bigger piston force is capital F upon area is A2. So ratio small f upon capital F is equal to A1 upon A2. Okay. Now the diameter is, smaller piston has diameter D and capital D. So area is nothing but pi by 4 D square, and this is pi by 4 D square. Okay. So we will get the ratio F upon F is equal to D square upon capital D square. So correct option is option C. Okay, so basic equation is the Pascal law equation, force upon area. Okay, refer the third question. The ratio of area of cross section of two pistons in a hydraulic machine is 1:15. Find the force that should be applied on the narrow piston to overcome a force of 120 Newton on the bigger piston. Okay. So this problem is again on the hydraulic press. So this is the force on the narrow piston, which is the smaller piston. Let us take F1. On the bigger piston, the force is given, which is a 120 Newton. Okay. So we have to find out what is the value of F1. So this cross section area, it is A1. For bigger piston, it is A2. So we have the equation, pressure is same. So F1 divided by A1 is equal to F2 divided by A2. Okay. Now from this we can write the equation. A1 upon A2. So you can take this A1 on this side, take F2 on the left side. So it is F1 divided by F2. Okay. Now A1 upon A2, this ratio is given. So cross section area of two piston is in the range 1:15. So A1 upon A2 is 1:15. So 1 by 15. From this we can find out F1, which is F2 into 1 upon 50. So F2 is 120, 1 upon 50. So this is 8. So F1 is equal to 8 Newton. So correct option, it is the option D. So this is how we can solve the problem on the Pascal law. Now next we will solve the problem on the surface tension. Okay, so refer the first problem on the surface tension. The sphere of influence has a radius of about. So we have just seen the sphere of influence. Its range is 10 to the power minus 9. So this is the radius for sphere of influence. So this is one molecule, and this is the sphere which is drawn around this molecule as a center. So radius is equal to the range of molecular distance. Okay. So this range is nothing but the radius, and which is 10 to the power minus 9 meter. Okay. Next is small drops of the liquid acquires the spherical shape because of the reason. Option A is of the gravitational force acting on the drop. Second is of because of the atmospheric pressure. Third is the volume of spherical drop is minimum. And last is the liquid surface tends to have minimum surface area. Okay. And the correct reason is small drops of liquid acquire spherical shape because of liquid surface tends to have the minimum surface area. Okay. And minimum surface area is possible only for the spherical shape. And therefore, we have the liquid droplet having the shape spherical. So reason is minimum surface area. Okay. Second question is surface tension of the liquid is due to cohesive force, adhesive force, tension in the liquid, or the atmospheric pressure. Okay. So surface tension is because of the cohesive force. Okay. Third is a brush is dipped in the water and removed. The hair of the brush cling together due to the first is the force of attraction between the hair. Second is the characteristic property of the hair, viscosity of the water, and surface tension of the water. Okay. Cling means they stick together when we dip the brush in the water, and they cling together. Reason is the surface tension of the water. Okay. Okay. For the fourth question, as the temperature of the liquid rises, its surface tension remains same, increases, decreases. So surface tension is inversely proportional to the temperature. So as temperature increases, the surface tension it will decrease. Okay. So this is the third option. Okay. Next question is at critical temperature, surface tension of the liquid is. So always remember at critical temperature, surface tension of the liquid it is equal to 0. Okay. So this is one special case for the surface tension. So correct option is option A. Okay, now refer the next question on the surface tension. The surface tension of the liquid is 10 to the power 8 dyne per centimeter. It is equivalent to, so we have to select the correct option. So surface tension, it's a SI unit, so it is Newton per meter. Okay, in the question it is given as a dyne per centimeter. So what is given? 10 to the power 8 dyne per centimeter. Okay, to solve this problem, we should know the relation between dyne and Newton. So 1 Newton, this is equal to 10 to the power 5 dyne. Okay, so therefore 1 dyne, it is equal to 10 to the power minus 5 Newton. Now put this value in this equation. So it is a dyne, so convert that into Newton. So 10 to the power 8 into 10 to the power minus 5 Newton divided by centimeter is 10 to the power minus 2 meter. Okay. So from this we will get the answer 10 to the power 8 into, this is minus 5 and minus 2. So the remaining is 10 to the power minus 3, and this is equal to 10 raised to 5 Newton per meter. Okay. So correct answer is option C. 10 to the power 8 dyne, it means 10 to the power 5 Newton per meter. Okay, so for the next question. A needle of 0.05 meter can just rest on the horizontal surface of the water without weighting. What is its weight? And the T means surface tension. It is 7 into 10 to the power minus 2 Newton meter. Okay, so we have to find out what is the weight of the needle. So let us take, this is the free surface of the liquid. This is the container, and this is the needle. Okay, so needle is floating on this, on the surface of the liquid. So when needle is floating, the liquid will offer the surface tension. Okay, so surface tension, we have the formula T divided by force upon L. Okay, so this is the force of surface tension. Now in case of needle, we have to take the length on both the sides. So this length is L, and again this length is L. Okay, so this total length will be F divided by 2L. So this is for the needle which is floating on the free surface of the liquid, and here F is nothing but the weight of the needle. So W upon 2L. Okay, so W is equal to, just multiply T into 2L. T value is given, which is 7 into 10 to the power minus 2 into 2, and length is 0.05 meter. And from this, the answer is equal to, this is 7 10 to the power minus 2. This is 0.1, 2 into 0.05. Okay, 0.7 10 to the power minus 2. Okay, and it means that 0.0 again 0.7. This is Newton. Okay, so correct option, it is option C, 0.007 Newton. Okay, so the formula required is surface tension is force upon length. For the needle, consider the length 2 times its original length. So it is 2 into L. And here force is nothing but the weight force. So weight divided by 2L. Okay, this is the basic formula. Simultaneously note down the important formula. And if you want, you can take the screenshot for the question. Okay, refer the next problem. A thin circular plate of radius capital R has a hole of radius R smaller at its center. Float at surface of the liquid having the surface tension capital T. The force of surface tension acting on the plate is, okay. So here the shape given is, the plate is circular and it is having the circular hole at the center. So circular hole, it has radius R and the plate has outer radius capital R. Okay. So what is the force of surface tension? So we have the equation surface tension is equal to force upon the total length. Now here we have to consider, if this is a floating on the liquid, liquid will offer the surface tension on this periphery and again on the outer periphery. So we have to consider both this length. Okay. So here length is equal to, inner periphery is 2 pi r and outer periphery is capital 2 pi into capital R. Okay. So this is equal to 2 pi in the bracket R plus capital R. This is the total length and the surface tension T. So F is equal to surface tension into length. This is equal to T into 2 pi R plus capital R. Okay. So correct option is option B. Sorry, this is minus R. So correct option is option C. T into 2 pi in the bracket capital R plus small r. Okay. Okay. Refer the next question. The potential energy of a molecule on the surface of the liquid compared to that of a molecule inside the liquid is smaller, same, greater, or zero. Okay. So any molecule is nearer to the liquid surface, that is a free surface, will have the higher potential energy compared to that which is at the bottommost point. So correct option is option C. Okay. Next question is, the surface tension of a liquid is capital T. The increase in its surface energy on increasing the surface area by A. Okay. So we have the equation for surface energy is equal to surface tension into the area. Okay. So if I increase the surface area by capital A, increase in the surface energy will be T into A. Okay. So correct option is option B. So just remember this equation for surface energy or the work done, W is equal to T into A. Okay, refer the next question. work done in blowing a soap bubble of radius 5 centimeter. So soap bubble has initial radius 5 centimeter. Surface tension of soap solution is 30 into 10 to the power minus 2 Newton per meter. So we have to find out the work done. So work done is stored as a surface energy when we are blowing the soap bubble. So work done has a formula T into A. Now T into, now for this soap bubble, so soap bubble is nothing but the hollow sphere. Okay. For the hollow sphere, we have to consider the two surface area. One is inner surface area and the outer surface area. Okay. So surface area formula for sphere is 4 pi r square, and total surface area for the soap bubble, it will be 2 times. So here capital A is equal to 4 pi r square into 2. So this is only for the soap bubble and not for the water drop. So this is surface tension is given 30 into 10 to the power minus 2 into 4 pi r square. So r is 5 centimeter. So 5 into 10 to the power minus 2 meter square into 2. Okay. So this is equal to 30 into 10 to the power minus 2 into 4 pi. 5 square is 25. 10 to the power minus 2 in square, it is minus 4 into 2. Okay. So 25 into 400. Okay. So 100 into 2, 200 into 30. So this is 6,000 into minus 2, minus 4, minus 6. Into pi. Okay. So this is equal to, W is equal to. So from 6,000, we can write 6 into 10 to the power 3. Okay. So 6 pi into 10 to the power 3 into 10 to the power minus 6. So 6 pi. So 3.14 into 6. So this is equal to 18.84 into plus 3 minus 6. So it is minus 3. Just base is same. So add the power. And the correct option, just shift this decimal place on the left side. So 1.884. So 10 to the power minus 2. Okay. So this is the work done. Now the correct option is option B. So formula required is for surface energy, and for the soap bubble, surface area is 4 pi r square, but for the bubble, considered inner surface and the outer surface. So multiply here by the factor 2, and this is not for the water drop. Okay, refer the next question. A spherical liquid drop of radius capital R is divided into 8 equal droplets. Its surface tension is capital T. Then work done in this process will be. So work done, this is equal to T into area. So what is given? Spherical drop of radius R. is divided into 8 equal droplets. The surface tension is T, then the work done in this process will be. Okay. So initially in the theory, we have seen the formula when we convert a single drop into multiple drops. So work done to split a liquid drop of radius r into n identical droplets. Okay. So here you can see number of drops n. So here n is equal to 8 in our problem. Okay. So you have to remember this formula. W is equal to 4 pi r square t n raised to 1 by 3 minus 1. Okay. So work done is equal to 4 pi r square capital T, n is equal to 8 raised to 1 by 3 minus 1. So 8 raised to 1 by 3, so it is 2, 2 minus 1, 1. So 4 pi r square T. This is the work done when single drop is split into 8 droplets. So answer is 4 pi r square into T. So here the correct option is option C. It is 4 pi r square into capital T. Okay. Now refer this theory question. A liquid does not weight the solid surface if the angle of contact is, okay, so 0, obtuse, acute angle, or 90 degree. So liquid does not weight. So here, if theta is equal to 90 degree, so liquid does not weight the solid surface. For the mercury and glass, Fc and Fa are cohesive and the adhesive forces. Then the correct relation is Fc less than Fa, Fc greater than Fa, Fc equal to Fa, or Fc is equal to 0. Okay. So for mercury, the cohesive force is always greater than the adhesive force. Okay. And therefore, we observe the convex meniscus. So correct option is option B. Fc is greater than Fa. Okay. Now refer the next question. This is on the capillary action. A capillary tube, when immersed vertically in a liquid, records a rise of 3 centimeter if the tube is immersed in the liquid at an angle 60 degree with the vertical, then length of the liquid column along the tube will be. Okay. So in case of capillary action, when we immerse a vertical tube, and this is the rise of the liquid. So this rise of the liquid is h. If I incline the same tube, having the inclination alpha with the vertical line or vertical axis, then this length of the liquid rise in that tube. So this is given by L is equal to H upon cos alpha. Okay, so this is the formula. When we incline the tube by angle alpha, H is the original height of the liquid rise in the vertical tube. So here original rise, it is given as a 3 centimeter, and the inclination is alpha, which is 60 degree. So it is a cos 60. So 3 upon cos 60 is 1 by 2. So take 2 in the numerator. So it will become 3 into 2. So this is 6. So L is equal to 6 centimeter. Okay. So length of the liquid column along the tube, it will be 6 centimeter. So correct option is option C. Okay. Now refer the next question. Water can rise up to the height of 12 centimeter in a capillary tube if the tube is lowered to keep only 9 centimeter above the water level. Then water at the upper end of the capillary tube will overflow, will form the convex shape, will form the flat surface, or it will form the convex surface, concave surface. Okay. So in case of water, so original water level rise, it is 12 centimeter. So original shape is concave shape. Okay. If we decrease the height of the capillary tube, okay, this height is just 9 centimeter. So water will reach to the topmost point. Okay, and because of the atmospheric pressure, it will form the flat surface. So correct option is it will form the flat surface. Okay, so these are some questions on the surface tensions. We will see the basic theory about the capillary action, capillary tube. So initially we have seen the theory up to the angle of contact. Okay, now let us see the relation for shape of the liquid droplet on the flat surface. So shape of the droplet depends on the surface tension and the angle of contact. Okay, so here I have shown one image and I have shown three forces. One is T1, second is T2, and third is the T3. Okay, and this is the liquid drop on the surface of the solid. So T1, it is the surface tension between liquid and solid. T2 is the surface tension between air and solid. T3 is the surface tension between liquid and air. So all these forces are tangential at the surfaces in contact, and for equilibrium of the drop, this relation will be satisfied. The force T2, it is equal to T1 plus T3 cos theta, or we can write for the cos theta. So cos theta is equal to T2 minus T1 divided by T3. Okay. So this is the relation for the equilibrium of the drop. Now the first condition is for acute angle. So theta is less than 90 degree. The force T2 or the tension T2, it should be greater than T1. and T2 minus T1, it is less than T3. Okay, so if this numerator is less than the denominator, then and only then cos theta is positive and theta angle will be acute angle. Okay, an example is water on the glass. So for water drop on the glass, theta is less than 90 degree. Now second is the condition for obtuse angle. So you can refer the figure. So here T2 is less than T1 and T1 minus T2 is less than T3. So our basic formula is cos theta is equal to T2 minus T1 upon T3. Okay. So here T2 is less than T1. So numerator is negative. And T1 minus T2 is greater than T3. So in this case, theta angle is the obtuse angle. So theta is greater than 90 degree. And the example is mercury on the glass. So if you pour the mercury on the glass surface, then the droplet will be formed having the angle or angle of contact is greater than 90 degree. And third condition is if T2 minus T1 is greater than T3, so numerator is greater than denominator, then cos theta is greater than 1, and which is the impossible condition for the cos function. And in this case, drop will not be formed and liquid will just spread over on the solid surface. Okay, so this condition is possible when cos theta is greater than 1. So basic relation is cos theta is equal to T2 minus T1 upon T3. Now what are the factors affecting the angle of contact? First is the nature of liquid and the solid in contact. Second, impurities present in the liquid. It will change the angle of contact. And third is the temperature. So any increase of temperature of the liquid will decrease the angle of contact. So there is inversional proportionality. So if the temperature increases, the angle of contact, it will decrease. And second is factor affecting the surface tension. First one is the impurity. So in case of impurity, when soluble substances like sodium chloride is dissolved in the water, surface tension will increase. Okay. Second, when the substances like phenol or the detergent is mixed with the water, surface tension will decrease. So when we mix detergent or a phenol, surface tension of the water will decrease. Due to this, water makes a good contact with the cloth fabric and enable to remove the turf stain. Okay. And last is the when insoluble impurities added into the water or the mercury, surface tension will decrease. Okay, so if you add insoluble impurities in the water or the mercury, surface tension will decrease. Due to this, cohesive force of that liquid will decrease. Okay, so when we add any impurity, it will decrease the cohesive force, and because of that, surface tension will decrease. And the last one is the temperature. So in most of the liquid, as we increase the temperature, surface tension will decrease. Okay, and there is one exceptional case, which is the molten cadmium or the molten copper, where surface tension will increase with increase of the temperature. Okay, so remember this special case. So general relation is for temperature increase, surface tension will decrease, and the exception is molten cadmium and the molten copper. Okay, now there is a relation for pressure inside a drop and pressure inside a bubble. Okay, so when liquid drop is formed, the pressure inside, it is given by the relation. So Pi minus P0 is equal to 2T upon R. So P0 is the absolute pressure. So basically, this relation is for the gauge pressure, 2T upon R. Okay. And when soap bubble is formed, the pressure is 4T upon R. So remember these two relations, pressure inside the liquid drop and pressure inside the soap bubble. For liquid drop, it is 2T upon R. So this is for the drop, and 4T upon R. This is for the bubble, that is a soap bubble. Okay. Now next is the capillary action. So when tube having the bore diameter up to 1 mm. So capillary action is observed for the tubes having the diameter up to 1 mm, and tube must be open at both the ends. Okay. So if this tube is deep or immersed in a liquid which weights the surface of the tube, okay, then liquid rise in the tube. So if the tube is deep in the liquid which does not weight the surface, then liquid level will drop. Okay. So here first is the rise of the liquid in the capillary, and this is for the water, because water will weight the surface of the glass. And second, this is called as mercury fall. Okay. So or the capillary fall, and this is observed for the mercury which does not weight the surface of the glass. Okay. So capillary fall or capillary rise, this is given by the equation H. So H is equal to 2T cos theta divided by R rho G. Okay, T is the surface tension, theta is the angle of contact, R is the radius, rho is the density of the liquid, and G is the acceleration due to gravity. Okay. So for capillary fall, this is observed for mercury. Theta is the obtuse angle. Okay, and therefore cos theta is negative. We will get H as a negative. Okay. For capillary rise, this is for the water or any other liquid that weights the glass tube. Theta is acute angle, so cos theta is positive, and H will be the positive. Okay. So this is the H. H is measured with respect to the free surface of the liquid. And in case of capillary fall, this is the negative H. Okay. So basic relation for rise or fall is 2T cos theta divided by R rho G. Okay. So last we will see one problem on the capillary action. Okay, so these are two questions. They are on the pressure inside the soap bubble and pressure inside the drop. So excess pressure inside the liquid drop of radius R and surface tension T. So in case of liquid drop, the pressure is 2T upon R, just we have seen. And the excess pressure inside the bubble of radius R, the answer is 4T upon R. Okay. So remember these two formulae. For drop 2T upon R, for bubble it is 4T upon R. Now here this is on the capillary action. Flow of ink in the refill of dot pen or the ball pen is due to, the answer is capillarity. Okay. So ink will flow inside the refill. So this is just because of the capillary action. And the meniscus of a liquid is concave if P1 and P2 are the pressure just above and below the meniscus. So this is the liquid meniscus formed inside the capillary tube. This is the pressure which is just above the meniscus, and this is the pressure just below the meniscus. So P1 and this is a P2. Okay. So to form the concave meniscus, P1 has to be greater than P2. Okay. So correct option is option B. Okay. The last question. A capillary tube of radius r can support a liquid weight 6.28 10 to the power minus 4 Newton if the surface tension of the liquid is 5 into 10 to the power minus 2 Newton per meter. The radius of the capillary must be. Okay. So here surface tension will support the complete weight. So we have the equation for surface tension. This is equal to force upon the length. Okay. Here force is nothing but the weight of the liquid. And what is the length? Length is nothing but total circumference. Okay. So this is the point which is in contact with the wall of the tube. Okay. So at this point, the surface tension will act, and this surface tension or the force because of that surface tension will act on the complete periphery. Okay. So here a length is equal to 2 pi r. So F upon L is the surface tension. F is nothing but the force, and force is nothing but the weight of the liquid. Okay. So W divided by 2 pi and R is equal to, so W is given, this is 6.28 10 to the power minus 4, and R is equal to 5 into 10 to the power minus 2. Okay. 2 pi is nothing but 6.2. So we can cancel out this. 1 by 5 is 0.2 and 10 to the power minus 2. Okay. So this is equal to 2 into 10 to the power minus 3 meter. So correct option is option D. Okay. So remember this formula for the capillary tube surface tension. F upon L, and L is nothing but 2 pi r, which is the circumference of that tube, and W is the weight of the liquid. Okay. So in this module, only one part is left, and that part is the fluid flow or the fluid motion. Okay. So we will discuss this fluid motion and we will solve the objective type questions in the next session. Okay. So today we will stop here.